Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome to day 40, Vanilla Math Man's Math Help Streams. Yeah, we're holding it down for another week, right? Yeah, getting courses done. It's the end of the month, sort of rush here now. Uh, yeah, it's constant going these days here now, but still making time for a bit of a break here to talk about some mathematics. And some good video teaching. Make sure that people feel like we're back in class a little bit. Give people a chance to interact with me live and in person. Or as in person as we can be. Given the circumstances. As Canadian as possible, given the circumstances. Right. That's our motto. That's a good one. Today, now for the title, you'll notice that I've called it symmetrical show and tell. Now that's actually a little bit of an indication of one of the topics I'm going to get to in a bit, as we can see over. Now, see stage directions. Right here, lines of symmetry. Yeah, we're going to be doing those today. And when we do, I'm going to be bringing up a few objects that I've sort of accrued over my vacations, and we'll discuss the symmetry of those. Um, I one of the main things I like to do when I go traveling, other than hiking and food, is markets. Right now, when it comes to shopping, shopping's okay. Like I don't mind going to big box stores or going to like malls and stuff like that, but that's not really my jam. Right? It's fine. I'll do it for a day or so. Right? But the small little like boutique shops or even better markets with stalls. Boy, I love that stuff. Probably my literally my favorite place that I was when I was traveling was well, it doesn't really count as traveling because I lived near there for a while, but Camden Market in London. Boy, that still goes down as one of my favorite places on earth. And I will definitely show pictures of that place and talk about the incredible food and various trinkets and things that I got there. Got a very, very nice pair of shoes there that I still use as my like primo dress shoes. I bought them for like 80 pounds at a cobbler in the horse stalls market. And yeah, they're normally like, I don't know, several hundred pounds easily. But they're quite nice. That's still my go-to dress shoe. That refurbished pair of shoes that I bought in London. Anyway, um, seeing I now in the background here is one of the places that I've shown already on stream, right? And let's see. This is I like this picture of the market because of this ATV here behind my head. I find it amazing, right? Like, well, I'll show you. I'll see if we can figure out where this market is. Hold on. Maybe you can get it from. See, this picture here is not. Well, that's roughly the same, right? Like, it doesn't really tell you what city it is, but maybe, yeah, maybe this one. Maybe this one will help. Let me scroll. Oh no, no, come on, OBS, come on, you can do it. There we go. Yeah, let me scroll it so we can see a little bit better down there. But you can see now up behind my stream starts soon. This is a small marker with a view of the Parthenon, right? So we're back in Athens again, right? Because everything in Athens has a view of the Parthenon. Hi, Teach. Hey, Garad. Thank you. Welcome. Glad you could join me. Just doing a little bit of a pre-show here, but then we're going to get into talking about some mathematics. But we can see here we are indeed back in Athens in these pictures. And when I was in Athens, I went to this open air market that's sort of like in the shadow of the Parthenon. And yeah, I managed to get some very nice trinkets. My favorite of which, one of my favorite things that I got is just this knife here, right? This looks like a plain old knife, doesn't it? But this has been extremely useful for me. I mean, just listen to this. Listen to this satisfying. Listen. Oh, okay. Chroma key is going crazy. Listen. Ah, right? And look how firm that is. That doesn't budge. It doesn't budge at all, right? It's really good. It's a good solid construction. And more importantly, the thing that I use much more than a knife is we flip out this side over here, right? Look at that. It's a bottle opener, a saw, and a standard screwdriver on the tip, right? Really, really useful. That saw, I got to tell you, every hike I go on, this knife accompanies me. because that saw is massively useful. I've used it to cut loads of firewood. It's very durable and sharp for how small it is. This is simply for spending 10 euros on this. This is the best, well, maybe the second best 10 euros I ever spent. The best 10 euros I ever spent might have been a pre-release early access copy of Minecraft back when Mojang was an unknown uh, little Swedish company, and I paid 10 euro to buy that entire game forever. Right, that was nice. I also do have a very beautiful small little object that I bought in Sweden. Another at another market, sort of like, well, this was more of like a boutique shop district, sort of like downtown St. John's kind of, but it was in Stockholm on one of the small islands near the center, and it was this very pretty. Look at that. This is a piece of Aboriginal art that was out there. My parents collect art like this. Uh, right? But this is like soapstone and then antler down here, right? Very beautiful little piece of sculpted, uh, you know, native Swedish art, I guess that I bought in Stockholm. Thought that was quite nice. That'll be part of my show and tell for today. But we're not. Don't worry, Esther. I see you there in chat. We're not going to be talking about the number of lines of symmetry of a shape like this. We're going to keep it a little bit more straightforward. We're probably going to use shapes a bit more like this one, right? Like this coin here. Bert, if you're Albert Einstein, if you're in chat there and you want to get a lead on it, this is a coin that I'm going to be asking you to figure out where it's from a bit later. You can see there's a hole through it, right? There's a hole through the center, so that'll help you. It's silver. There's little hearts around the edge of it. There's like a crown on top. I don't know. We'll find out. We'll find out what that one is. Maybe someone can get a bonus mark or two for knowing where that coin is from. Kroner. It is Kroner. Yeah, it is. It is a type of Kroner. That's why there's a crown on there. That's right. But which one? That's my question. This one, I believe this one is still legal tender actually. That's a hint. It's not one of the places that has adopted the euro. I can squeeze that sentence out one way or another. Anyway, I should still have my stream start soon up there, because it do. Stream is starting soon, right? Danish? Yes, that's right. It is. Yeah, that was quick. That was a quick one, Esther. Yes, that is Denmark. It's a Danish krone. I didn't spend much time in Denmark. I think I believe I was just in the Copenhagen airport for a stopover. A nice open face salmon sandwich I had there. Apparently that's like a big Danish thing, right? This open face salmon sandwich with like cream cheese, I think. Anyway, can't remember exactly how it went, but it was good. Anyway, without further ado or without further rambling, you have a lot of them? Oh, okay. Yeah. I guess your husband probably. Yes, of course. Your husband would have Danish krones because of from Greenland. Of course, yes, because Greenland uses Danish money. Yeah, that makes sense. Yeah, this is chump change here. This is like what, like 10 krones? I don't two. Look at that. Although about 10 to a dollar, right? So two is still like this is like 25 cents or so probably. But anyway, yeah. So let's pop over to some of the work that we're going to talk about today. Esther, seeing you're there in chat, I guess I will start off with yours. The converting units of area. I have done that one a fair bit recently. Renetta, if you are in chat, you can sound off, and I will get to those before the stream's over. If not, I mean, I've done those occasionally recently, so you might even have other ones you could look at. Boy, my hiccups. These hiccups are, boy, this plagues me. I don't know why hiccups so bad. Anyway, yeah, so I'll start off with properties of quadrilaterals. So that is Math 3102B. And I'm gonna take a little bit of a look at the study guide first and just talk about some different quadrilaterals. Then we're gonna go do a few questions from the text. Okay, so I'm gonna switch on over here to the document display. Here we go. So we see over on the side, over here, right? Oh, my cursor. There we go. Now we've got my cursor. So I skipped down a little bit through the unit. We see the unit starts up here, right? But Esther, this part here is one that we've talked about already before, the measure of interior angles. But I guess it's reasonable for me to spend a second or so talking about that one. So let me just do an example of that, and using using another piece of show and tell that I'm going to be showing today. So this sort of symmetrical show and tell is going to be a theme throughout today's episode. I think it's the first time I called this an episode, you know? So this is Math 3102B Unit 2. Oh, we're a bit off. The document cam sometimes hard to position. Sometimes hard to position the boom cam exactly in spot here. But this coin, this is another one. This is one that I used frequently because this is 50p from UK, right? So 50p currently is about what? This is probably like 75, 80 cents right now, right? Because Canada's money is not as good, it's not as strong as it once was, but they're not doing that bad. You see on here, this one actually says new pence. This one wasn't in my coin collection. I actually found this one in a coin collection that my grandfather gave me, which contains some coins from his travels. Like he's got some from Africa, some from Israel. Um, I haven't been to quite as many places as my grandfather has. Although I've been to lots of places in Europe, so maybe, it'll even out eventually. But this one, as we see here, this one was actually from 1969, which is why it has new pence on there, because Britain didn't have hasn't had a decimal currency for all that long. Previously to that, there was a sort of shilling system where it was, I believe, out of a gross, it was 144. I think. I can't remember exactly how that one goes, but I did teach a lesson to some of my students in the UK about that. But anyway, this is called new pence because this was briefly after UK transitioned to a decimal currency, which is more similar to the currency in Canada or the US and stuff like that. But the reason I'm picking this coin to outline is because this is a seven-sided figure. I called it a septagon first, which is wrong. I believe it's a heptagon, I believe is what a seven-sided figure is called. But anyway, so if we have a seven-sided figure like this, right? So I tried to outline it roughly here. We can find the measure of each of these interior angles because we know a coin like this is a regular shape, which means all seven of these faces are the same length, right? So we see the measure of interior angles m over here on the side is equal to 180 times n minus 2 divided by n. Now what the heck does that mean? So the interior angles are going to be 180 times the number of sides, subtract 2, divided by the number of sides. Now you have seen these ones before, which is why I'm going over it kind of quickly. But what we'll have then is m for this shape is going to be 180 times 5 divided by 7, right? Because there's 7 sides to this heptagon. So then m is going to be 180 times 5. Well, I should know that off the top of my head. That's going to be, what, 900? 900 divided by 7, I'm not going to do in my head. 128.6. So it's going to be 128.6 degrees. So what that tells us is that each of these angles here, like this angle here, this angle, this one, this one. The 50p is a bit curved as you're seeing, right? So it's not quite as rigid as I would have hoped. But all of those angles are 128.6 degrees, right? Now, the reason why this works and the reason why we're using 180 and n minus 2 is because every two-dimensional shape, every regular two-dimensional shape, or even really not regular ones. So anyway, any two-dimensional polygon can be represented as a number of triangles sort of mashed together, right? So a seven-sided figure is going to be 5 triangles, right? Because we could see this by sort of drawing. Let me outline another one over here. So to take one like this, right, it's going to be a little small on the camera here because the coin is not all that big. But if I take a straight edge, I can see, right, if I join this corner and this corner up, that makes one triangle. And then now for each additional corner, there's another triangle. That's another triangle. That's another triangle. And then this last one here makes 2 triangles, right? So we can see from this that a seven-sided figure is 5 triangles. right? And since a seven-sided figure is five triangles, that's why we've got this one over here. And for the same token, it's much easier to think of, say, a square, right? A square is quite obviously two triangles. A triangle is one triangle. And then as you keep going, you keep adding another triangle each time, hence this rule here. Okay? But you have seen that one a bit before. I'm going to scroll down now, though, and I'm going to talk about the next section, which are sort of these properties of different types of quadrilaterals, right? So the main four that we are going to be talking about, of course, are the rectangle, square, the trapezoid, and the parallelogram. They specify an isosceles trapezoid, which has two equal sides, right? But let's look at, if we look down through each of these, we see that some of these are categories of the other ones, kind of. The terminology is actually not a huge part of this course, although you are still going to be expected to know the terminology. But say the terminology when you were quizzed on it was, I believe, Math 2017, which was one of the prerequisite maths. Um, but we know that, say, a rectangle has four right angles, opposite sides are parallel and equal in length, and the diagonals are equal. We know that those diagonals are equal to each other. But say, then we know that a square, well, has four right angles, opposite sides are parallel, all sides are equal, diagonals are equal. So there's only one extra bit there, isn't there? There's just that all sides are equal. This bit is new compared to the rectangle, but the rectangle has all the rest of them. Right? So from looking at these properties, we know that, say, a square is a type of rectangle. It's just a special type of rectangle. In the same way that a rectangle is just a special type of parallelogram. Right? Because a parallelogram has opposite sides equal. Well, diagonals are not equal, it says here. Well, that's not quite true. Diagonals might be equal, they might not be equal. Right? So I see what they're going for here, but realistically, a rectangle is a type of parallelogram because this last bit, diagonals are not equal, actually isn't a requirement, right? But it is going to be important to know these guys and to know the notation that we're using here, right? Like, say, in the parallelogram, these symbols, which you've seen all these before, right? The single arrow lines are parallel. The double arrow lines are parallel, just like up here, right? But then also, if you look at the trapezoid, like the notch ones, this side and this side are the same length, but they're not parallel. As we see, they're quite clearly converging, right? And these angles, which are both marked, we know that those angles are going to be the same as well, right? But what I'm going to go on to now is I'm going to look at a few questions from on this topic, which are going to be, let's see, we're going to do page 241 in the textbook. So page 241. Let me scroll back up. This is I left it on the second page that I want to get to. So we're going to get to that one there in a second. First, I'm going to go down through a few of the types of questions that you're going to have to do in this unit. So that's going to be these ones here. So these are all going to use properties of quadrilaterals, but it's all stuff that we've seen before pretty well. This is page 241, and I'm going to start with it's question 1. All of it's going to be question 1. We'll start with question A. Right, so we see our rectangle over there on the side. Tell you what, I'm going to draw it out. Maybe I won't do every single one of these, but I will draw out the rectangle so that I can label it. Once we can label it, it becomes a bit clearer, I think, what we are talking about. There we go. Keep my paper roughly centered there. Let's see. A, B, C, D. Good, nice counterclockwise ordering there. So AB is 3 inches, so we know this is 3 inches over here. We know AD is 4 inches, 4 inches there. AC is 5 inches, so from here to here. It's tough to label that one on here, but I'll put down 5 inches in there. Let's see. And then the other ones, okay. So the other ones now we're going to have to figure out which ones those are. Now we're told from the start that this is a rectangle. Right? And it's extremely important that we were told this was a rectangle, because if we weren't told that, I know it seems pedantic, but like I always say, or, needlessly precise, I guess. But like I always say, don't trust the way diagrams are shaped. Trust the symbols that you're told, right? So if, for example, if this was written as a right angle there and a right angle there, well, then you can start saying, oh, hey, this is a rectangle. Like if we were told all these right angles. But we were told at the top that it is a rectangle, so we know that those have to be right angles. But this one's relatively easy. We're not even being asked about the right angles, or the angles here. We're just being asked about the sides. So side BC, well, side BC has to be 4 inches, right? Because side BC is opposite side AD, right? Side CD, well, that's opposite side AB, so that one is going to be 3 inches, right? And then side BD, well, BD is a diagonal. We're told the diagonals are equal, so that one has to be 5 inches, right? You're probably seeing now that these properties of quadrilaterals questions are relatively straightforward, aren't they? Right? Um, Say for the parallelogram, maybe I won't draw all these ones out because it's going to take a little while, and the questions honestly are these should be fairly quick questions, right? So if I was to do 1b over here, uh, QO, well, we see over here, right, in our shape, MQ is 5 centimeters, right? And we know that the diagonals go through, that they bisect the shape, right? Since we're told this is a parallelogram, we know that this diagonal and this diagonal, the point in which they meet is the exact middle of the shape, right? So since these are straight diagonals from the corners across, the place where they cross is the middle, which means if this part here is 5, well, guess what? This part here got to be 5 too, right? So that's side. I like to represent the line on top to show that it's, a line segment, say, for example, right? MO, I mean, this is all probably fairly straightforward here for you, right? But MO is, of course, now going to be 10. Well, that's not hard, right? Because we know that MQ is 5, QO is 5, so MO is 10. PO, right? PO goes from here to here, right? But we know we're told this is a parallelogram, which means this side is parallel to this one, and this one is parallel to this one, which means we know that this side and this side are equal, and this side and this side are equal, right? So we know that PO is going to be 9, same as the one opposite it. And then PQ, the province de Quebec, is going to be, well, PQ is going to be the same as QN, so that's going to be 7. Let's see. Let's do maybe one more of these ones. So let's pick the hardest looking ones. Let's go down here to these bottom two. Right? So for question E, yeah, I'll do EF, and then I think we can probably move on from this and get to the lines of symmetry that the title alluded to, or alludes to. Boy, got to watch my verb tenses. Like I call myself an English teacher. Isosceles trapezoid. Let's see. So SR, we're told that this side over here, that one's going to be 4 meters. So PQ, well, PQ has also got to be 4 meters, right? Because we know that in an isosceles trapezoid like this side and this side are equal. So we know that PQ is going to be 4 meters, just like the other one. Then we were told, let's see here, we're told that angle PTS, actually, you know what? I am going to draw this guy out. I'm going to draw this one out because I think it's useful to see it on paper here. I suppose I could have broke out my image editing skills and had this one cropped already and ready to go, but I didn't. So I do have some other ones ready to go though. So we're mostly prepared. I'd say like 95% prepared. 92 maybe. 91. That's as low as I'll go. All right, so this is T, P, Q, R, S. Okay, so we know that SR is going to be 4 meters, so we know that PQ has got to be 4 meters. That's not hard, right? So then PTS, so angle PTS is this one here, so that one is 85 degrees. Now from this angle, right, we see how all the geometry stuff, like properties of quadrilaterals or triangles or angles or whatever, it all is really the same topic, just with a few other shapes thrown in, right? So here now, angle QTR, well, how are we going to get that? Well, it's directly opposite. What do we know about opposite angles? Opposite angles are equal, right? So angle QTR has got to be 85 degrees, right? That's not hard. So angle PTQ plus QTR plus RTS plus PTS, well, that's a bit silly. That's a bit of a silly question, isn't it? Um, I'm just going to fill the other ones in, though. Like, say we wanted to get this one here in blue, right? Well, we know that this plus this makes 180 because it's a straight line. So this has got to be 85, so one's going to be 95, right? And this one here is going to be 95. But we know that if we go the full way around the circle, it's going to be 360, right? Of course it is, because we could go add them up, or, you can go 360 degrees, right? Like when you see an Xbox, you turn 360 degrees and then walk away, right? Isn't that the Twitch meme? If you turn 360 degrees and you're back where you started and you just bump into it, right? But don't tell Twitch chat that. They don't, memes are not about being correct. Although technically correct is the best kind of correct, as everyone knows. So angle QTR plus RTS. Hey, real angle RTS. Look at that. Real-time strategy. Bringing it back. We're bringing it back to video games. STP plus angle PTQ is going to equal 360 degrees, of course, right? Because you're turning 360 degrees and then walking away. Yeah, I guess this is probably a good place to stop with these ones, because I think these feel, at least to me, these feel like it's fairly well covered, because it's all basically the same topics that we've seen before. Just now, all of a sudden, we're using four-sided figures instead of just triangles. But I mean, all the angle properties, all the shape properties are the same as what we've seen, right? The real meat of this section that you're onto, Esther, is going to be the lines of symmetry, right? So that's sort of the newer topic, and that's on page 255. That's the page I'm going to bump over to. It's on more than just that, but I'm going to start off here. So actually, I'm going to leave question 3. I'm going to do, but I'm going to leave this one for a second because I don't think they're in a great order here right now. So what I'm going to do first is this question number 5 here. List 2D objects that you've seen in your classroom, in your home, or elsewhere that have one line of symmetry, 2 lines of symmetry, and an infinite number of lines of symmetry. Well, I'm going to, real talk now, I'm going to blow your mind a little bit. You have never seen a 2-dimensional object in your home or in your classroom. It's simply impossible. You know why? Because they're all 3-dimensional, because we live in a 3-dimensional space, right? Like 3 spatial dimensions and 1 time dimension. That's all we get. Right? In our reality, we only get 4 dimensions. Now, it's possible to conceive of realities that have more dimensions or fewer dimensions. So it is possible that there are creatures in the multiverse living in a place where there are 2-dimensional objects. However, we are not those. Okay? Now, you may have seen 2-dimensional representations of objects, or say a 2-dimensional figure drawn on an object, as I have done here, but you have never seen a 2-dimensional object. Okay? just to clear the air about the number of dimensions that we exist in for a hot second here, right? But I do have some symmetrical show and tell here, right? So I am going to break out a few objects that have different numbers of lines of symmetry, and we're going to take a look at how many lines of symmetry those things have. Like, say I was to pick this object here, right? This one. This object. Now this, I could get you to guess what community this is from. But that's going to be a bit tricky, and you can see it right here. That it was from Brussels. hear about the NASA test results of the partial universe where time goes backwards? That's amazing. The parallel universe where time goes backwards. I want to hear more about that. Yes, absolutely. Right? Like it's like the plot of I don't know. Was there a show where the plot was that a parallel universe had time go the opposite way? That would be amazing. I was thinking of Fringe for a second, but the parallel universe in Fringe just like didn't have any coffee or something stupid, right? And then this one kid didn't exist in it, so the dad went and stole him from the other one, and then it caused a whole. Anyway, I don't want. I just spoiled half of Fringe for you. I'm sorry. Oh my god, I'm gonna have to put a spoilers tag on this stream. Don't. The teacher just spoils TV shows for us. Anyway, this is some random gaudy little, I don't know, tourist trinket that I bought in Brussels. It's I don't normally buy like little things that are made for tourists like this. I actually needed to make change, so I went into a shop. I needed to get cash for something, so I just went into a shop and bought this and like broke a larger bill with it or something because they wouldn't make change. I don't know. Anyway, this cost me like this cost me that was I mean this must have cost like a solid €2 or €3 for this little piece of metal shaped like the Belgian Parliament or whatever it is. Anyway, that was the second city that I visited internationally actually as a traveling Canadian. First being London, second being Brussels, which to quote the movie In Bruges, right? It would be a nice city if it was somewhere good and not somewhere shit like Belgium. No, Belgium's wonderful. I just love that movie. It's a great movie. But anyway, if we look at a shape like this, right, from the top here, well, this doesn't have any lines of symmetry, right? Because a line of symmetry basically means if we took this shape and folded it over, is it going to fit over itself? And from this angle, it doesn't, right? Now, even not caring about the chain bit, the spire here sort of is off center. Like if this was over closer to the center, then maybe we could say, well, it's symmetrical left and right. But right here, it isn't. If we took it and turned it this way, oh, still the spire because it's on the front, right? It's still not symmetrical left and right. If you look at just the bottom, well, now we're getting some lines of symmetry. But that's because we're now looking at a rectangle, right? So say instead then that I had an object that was rectangular, like say this. Here's another small souvenir. I mean, these are pretty pedestrian, right? Well, I guess kind of the opposite of pedestrian because it's a train ticket, which means you weren't being a pedestrian. Hmm. Anyway, but this one is, it's roughly rectangular, right? So how many lines of symmetry does this have? Well, the reason I wanted to show this one is because these are, I can't get these right now, but who cares, right? This is just a ticket stub from a train that I bought in London in apparently 6th of January 2013. So this one's been kicking around for a while. If I was to take this, right, we can see the lines of symmetry because we can just fold it, right? You can fold it and you can see that it fits over itself. So if I fold it in half this way, well, it fits perfectly over itself that way, right? So we know that was a line of symmetry. Because that's what a line of symmetry means. It's just that we could take the shape and we can fold it and it fits perfectly. And if I took it and folded it this way, that's going to fit too, right? So there was a horizontal line of symmetry and there was a vertical line of symmetry. We saw both those. But how about I took it and tried to fold it corner to corner, like diagonally? What's going to happen there? What? That didn't quite work, did it? Let me try that again. Let me try from corner to corner and fold it. Corner to corner, from there to there, and fold. Well, that doesn't work, does it? No, it doesn't, right? Because we're seeing now that a rectangular shape, a rectangle has two lines of symmetry. So say I was to get a rectangle, maybe I'll use one that isn't all all beaten up and folded to pieces, like this three of clubs here. So if we were to have a rectangular shape like so, okay, you know what? Scratch that. It didn't come out very well. Okay. Say we had a math 3102B unit 2. So say we had a rectangle, which I'll just draw roughly. Right? So this has two lines of symmetry, right? Now imagine it was drawn more accurately than what it was. Okay, but we could take it and we can fold it in half down this way, like so. We can take it and we can fold it in half across this way, like so, right? But the diagonals, other directions aren't going to work. They're not going to fold over exactly. So this has two lines of symmetry. Just that easy, right? This is all we're really doing here on what page is this now? This is page 50, 255. Right? So that one has two lines of symmetry. Say instead we were to get something like now it was tough for me to find something that had exactly one line of symmetry. But say we had something this big, like say this pair of scissors here, like this, right? This pair of scissors, well, how many lines of symmetry does it have? Well, obviously I can't take it and fold it. I'm not quite that strong. I'm close. I'm getting there, right? I'm eating my Wheaties, so I'm getting there. But if we took it, if we could fold it like in half, well, that's not going to work, right? If we split it this way, that doesn't work. Say we took it and I put diagonal. Well, obviously the diagonals don't work. But if we split it right down through the middle here, then I mean, aside from this little ridge here, which we'll ignore for sake of argument, this is going to have one line of symmetry, right? Because the top side and the bottom side are symmetrical, but the left and the right are not, and there's no diagonal sort of lines of symmetry either, right? So an easy way to see one with one line of symmetry would be actually looking at a triangle, right? So say we had a triangle just like that. Right now, how many ways can I fold this triangle? Well, obviously I can't fold it. I can't fold it that way. If I was to take it and if I was to fold it across here, right? Say from this side over, that's not going to work, right? Because if I was to draw that line there, this side and this side aren't going to fold over each other evenly. If I go from this vertex, those two sides are not going to meet evenly. But this one, this vertex, it will. Right, so a triangle like this has one line of symmetry. And it's just this easy for the lines of symmetry unit, right? Because all it is just the number of faces that something has. But then, say we had something like, this, another coin. This is one that I haven't shown on stream yet. So Albert Einstein, maybe you can guess this one too. Actually, I had to. Funny enough, I know this one looks like totally dull and like an in circulation kind of coin, and definitely not a one that you would ever buy from a store. But I actually had to buy this one at a flea market. I think it was here in town actually that I bought this one because I left this country with basically no money from it, which is really too bad. Because right at the end, the very last bus I had to get to the airport, I had one coin exactly like this that was pristine, like it was shiny and gorgeous, and I wanted to keep that one. But it was the last bit of money to spend to get out of there, right? Yes, I believe. Yes, yeah, yeah. This one is still legal tender. Yes, but anyway, if we have a coin, right, or a circle, how many lines of symmetry does a circle have? Any hints? Central Europe. Um, I don't know. A landlocked country in Central Europe. Europe, Y-U-R-P, right? There's if you can see it on there, there's a lion on there. Oh, it's the country. Oh, the name of the country actually has changed. The name of the country when this coin was minted, and the name that's on this coin is actually not the name of the country currently. That's a big hint. But yeah, if we have a circle, Czechoslovakia. Oh, good guess. No, it is part of Czechoslovakia. Yes, but this coin was minted when it was Czech Republic, right? It's called Czechia now. But yes, that's also a good guess that it could be from Czechoslovakia, and it is from the former Czechoslovakia. So there you go. That's from coin from at the time Czech Republic, but now I believe Czechia I think is the name of the country. But a circle, right? We can draw as long as we go through the center of the circle, right? We can draw a line wherever. We can draw one here like this. We can do one here like this, right? And it still folds over. We can do one here like this and it folds over, or like this, right? Because any diameter that we draw of a circle is a line of symmetry. So a circle has infinite. Because every single twist you make, every single different angle that you go to, right? You can draw another line of symmetry through a circle. Okay. Yeah, I want to do question 6, then I'm going to go back and do question 3. I really want to do question 3 on the previous page because it's I got to tell you there are questions on your test exactly like that one, right? But I'm going to do that one on the computer here, right? But that's number 5, sort of, right? Number 6, you were asked to do 6A and B. 6C is a bit much, right? But hey, you can do that one if you like. Look up some flags and see what the symmetry is. Maybe I do that at some point. But the flag of Newfoundland and Labrador, which is we see there on the right, includes triangles. Identify the types of triangles used in the design of the flag. Okay. Now I did want to show this one partly because it asks us, does the flag contain one or more lines of symmetry? And does it? Well, we can see that it does, right? There's a line of symmetry in the Newfoundland flag goes through the middle here because the top and the bottom are symmetrical, but the left and the right are not, right? What types of triangles? Well, we see these triangles here are scalene because this side, and this side are all different shapes, whereas these ones are isosceles, right? Nor are these scalene as well. I think those ones might be scalene as well. Actually, I haven't actually sat down and measured them. It's an interesting. The flag is kind of, I don't know. There's mixed opinions on the Newfoundland flag, right? Because we did have the Republic tricolor, which honestly is more only popular now, sort of in retrospect, because that was like a flag that was used for a very narrow portion of like St. John's because of an Irish bishop, I believe, um, that had created it, but it never gained traction really outside the city of St. John's very much, or at least St. John's area. But this Newfoundland flag is supposed to represent, the province's British colonial history, and then moving forward to a new future, as hence the left hand side looking like a stylized sort of part of the Union Jack, and then this sort of yellow arrow pointing forward to the right, which is a little bit of a peeve of mine because when we see on the left here, the part of the Union Jack that is represented by just the blue here is more the flag of Scotland, right? And Scotland's a wonderful country. I've visited several times and would love to go back. But but as someone who's also a bit of a devotee of Newfoundland history, the most of the immigrants from Britain to Newfoundland came from the West Country, so they came from England and not Scotland. But you don't see the English because the English part of the Union Jack is the red sort of cross that goes through the middle, and that's the part that's left out here, right? Because that would be there, there, and then there. So it's an odd sort of consequence of the way the Newfoundland flag is done is that it's supposed to represent, our history and then moving forward, which is all well and good. But in doing so, it's sort of it's sort of representing maybe I don't want to say the wrong part of the history, but it's making an implication that is not really true, right? But still, I do enjoy I guess the theory behind the way the flag is put together. So identify the types of triangles. Well, 6A, like I said, is I believe they're all scalene actually. I could measure those. And B, one line horizontal through the middle. Okay, then Esther. But now to finish off this sort of symmetrical bit that we're talking about, the lines of symmetry, I'm going to show question 3 up here, which are these ones. Now, oh, hold on just a quick second here. I've got to I don't think, do I have that? Oh, I do have it open. I do have it open. Look at that. Okay. Okay. So here now, I'm going to switch over to my to the most versatile and powerful image editing software ever created, which is of course MS Paint, right? And now, oh, well, you can see that my cam is aimed a little bit high. I'm looking off the edge of my screen. There we go. That's better. So here we've got this question, right? Over here, these are all the different parts of it. And it tells us, back over, if we go back over to the document display, it tells us to copy each large quadrilateral triangle, quadrilateral triangle, copy each large equilateral triangle onto isometric dot paper. Well, guess what? I did one better. I copied it to Microsoft Paint, buddy. As shading so that each large triangle has 3 lines of symmetry. Okay, so we have to only add and not subtract any symmetry, only add, but end up with 3 lines of symmetry for each shape, right? And I'm going to tell you, I am going to go down through this one because there are questions on your test like these. But to get 3 lines of symmetry in a shape like so, right, we have to be going through each of the points, right? So the only possible ways to get 3 lines of symmetry in a triangle like this is through this vertex over to this side, which would be a line like so we're going to want one to be a line like so, right? This one here. We're going to want one to be a line like this one here. And we're going to want one to be a line like this one here, like so. So those are the 3 lines of symmetry that we're hoping to achieve by sort of darkening some of these squares. Right, so what I'm going to do is I'm going to grab the filler, the filling tool, right? And I'm going to start filling these ones through. Well, we've got this end one here, right? So we know that, well, basically, right, if we draw this line of symmetry, this one already works, right? Because the left and the right sides of that are already good. But if we draw this line of symmetry, well, this one doesn't work now, right? Because this part up here has that square shaded, but not this square down here shaded, or triangle, right? So what we can do, of course, is fill in this one. Now that we've filled in this one, well, now the line of symmetry that we draw through this point here, this one now works, right? Because this one corresponds to this one, and now it's symmetrical, right? I'm clicking on stuff like a pleb. You think I don't play World of Warcraft in my spare time, right? You got to use keyboard shortcuts, man. You can't click things on screen. Sort of a scrub. Anyway, and now to get the last one, right? We're gonna have to fill in this guy. And now we see that this works out, right? We've got our 3 lines of symmetry that we want. Because if we were to take our line tool, draw a line here, this one works, right? Because this half corresponds to this half, and this one corresponds to that one. By the same token, this one here works, right? Left and right work, and then those two correspond. Then if we do the same thing over here, those ones, this half and this half correspond, this one and this one corresponds. There we go. We got there in the end. Right, remove those. So now if we scroll back down to B here, I think you're going to see kind of that it's going to work out the same way, right? So we have to have 3-fold symmetry, sort of. So basically whatever we do to this sort of point, you got to do the same over here and the same down here, right? So unsurprisingly, take it and fill it in like that, then we can check, right? So like I was telling you, we are 100% definitely, you are going to see questions like this on your test and on your assignments and stuff like that. So when you get this shaded, it's always a good idea to draw your lines of symmetry and check. Now, do these all 3 work? Well, this middle one, those work, and those work. Yeah, we can see that all those lines are lines of symmetry, right? And unsurprisingly for C, well, guess what? C is done. C already has 3 lines of symmetry, right? I mean, we can take it, we can start going ham on it. Look at that. There we go. That'll do, right? The ones on your test don't allow you to just do that because I'll tell you, the ones that you'll see on an assignment or a test will say, by shading, X number of squares or of areas or fewer, right? So you can't just take the shape and be like, oh, I'm just going to shade in all of them and then get there. Sometimes that'll work, right? So for this activity, it could. Like I could just go back up and shade all of them. Or I could even shade it like that. That works too. That's symmetrical, right? There's loads of different ways you could do it. But anyway, the point is, lines of symmetry are through the ends of the shape, right? Easy. Okay, so now we're going to go back over. Stream starts soon. No, it's already going. How's about I change our background? Let's go. Yeah, let's go over to this shot here. I believe this one. I believe that that orange table there might actually be the one that I bought that knife at. I can't recall exactly which one it was, but it was. It was. I'm pretty sure it's in this shot someplace. And I will definitely show more pictures of other markets that I've been to. I do love those. Although I've noticed in going through that I'm not as much of a shutterbug as I thought I was. Like there's loads of things that I saw that I don't have pictures of. But hey, I mean, it's more important to live in the moment, right? I don't know. I like taking pictures too. But anyway, so we've done properties of quadrilaterals and lines of symmetry. I want to do, yeah, I'll do sine and cosine laws here now. Betty Ann, I don't know if you're in chat there, but I have, actually, I need to get some more paper. Okay, so, oh, don't mind my chroma key. It does its best, okay? It's really making do. All right, you're welcome. If you got any questions, Esther, about any specifics or anything like that, I mean, you know my email, so you can let me know. Um, let me know whenever you can if you're having any trouble with those, right? But yes, if you do, I know it's a little bit of time pressure, but if you do get the assignment finished today, or uh, or even for tomorrow, yeah, you'll be able to go ahead and then do the review sheet, which is very similar to the assignment, and then the test on Thursday. But that's totally up to you, right? You're doing really well for progress as it is, so don't push it. But if you're finding these units easy, which I think this one is relatively easy, right? Then you're able to go ahead and do that if you'd like. Okay, so the next one, yes, sine and cosine laws. I'm going to do a bit on those. So let's pop over back to my document display over here. So this is now Math 2101A Unit 3. We'll have it done for tomorrow, hopefully. Okay, great. Yeah. And if you have any questions, just drop those in my email, and I'll get to those as soon as I can. So Betty Ann, I know that we've been beating these topics to death a bit because I've been, but this course does have a final exam, right? Unlike some of the other ones that say like the one Esther was just doing. So you've got one more piece of work to go before this course is in the history books. I gotta say, the academic math courses in this ABE program are bar none. They're the hardest and longest and most involved courses that we offer, for sure. Like even the academic physics, I don't find to be as long or as involved as the academic math, simply because like the math courses have like 4 tests each, and then there's a final exam at the end and stuff. Whereas the physics courses and the chemistry courses and stuff like that even just tend to be like 1, maybe 2 tests. Anyway, for question 5 here, which of the following is not correct? Yay me. Yeah, yeah, it's too bad. But I mean, you're getting through them, right? And like I'm saying, I know this is only 2101A, right? So this is course like 4 of 9, but they don't really get any harder, in my opinion, because the difficulty level in the academic math is pretty much constant right from the start, right? So if you get over that initial hump of how much more difficult the first one is than the previous math, then I think it's all fairly even keel throughout the rest of it. But there is still a fair bit of number crunching involved. You know, I mean that was pun intended. Right, so which of the following is not correct for acute angle XYZ? Well, how's about I just write out the sine law as we normally do it? So A over sine A equals B over sine B. Right? So that's sort of the default form. So we know that say C, well this is C. So we know that C is correct. Right? So C is not the one that we're looking for. If we were to take it and flip it, which like I mentioned before, we are totally able to flip these, this would be sine A over A equals sine B over B, right? So this is a D, so this one is correct as well. So we know that. And now say we were to take these and cross multiply them. We would end up with B sine A equals A sine B, right? So that we see that the letters are different. That's the same as option B. So the one that you had to pick, or the one that's not correct, is actually A, because A has uh, x sine x equals y sine y. And the reason why that one is the incorrect one is because it has the same, right? It has the x here and the x here, the y here and the y here, which is not what you would actually get if you took it and cross multiplied. Let's see what. Now I can't recall. Have I sent you your mark on that activity yet? Yeah, you did really well on it. I've been, boy, um, yeah, working pretty fast to get through these this morning, but we got there. And if I haven't sent you anything, I'll notice in a second, and I'll send this to you after we're done talking here. But questions 11 and 12, I wanted to go over. Okay, so let me zoom out a little. Okay, so solve DEF if those things are true, and then draw a diagram. Okay, so how's about I go over to this display here, so we can see my stuff zoomed in a little bit more. So this is question 11. Okay. Was it above 80? Yes, it was considerably above 80. Oh, so I didn't send you your mark yet. Okay. It was definitely above 80. Okay, so solve this triangle if, what are the angles that we know? Okay, so this is going to be, I'm going to call this one D, this one E, and this one F. Which of those or which isn't really super important, but what is important is that the angles are, the sides are opposite, right? So this is going to be side D, going to be side E, and this is going to be side F. Boy, the hiccups have returned with a vengeance. So side D is going to equal 21.4. Side F, or lowercase f, is going to be 15.8, and this is centimeters, and this is centimeters. And then angle E here is 56 degrees. Now, Betty Ann, I will tell you that you got almost all the marks for this question, but what you did was you wrote your diagram incorrectly. You accidentally put this 21.4, you put it over here as side E. Now, if that was the case, drink lots of water. Yes, thank you. Um, if that was the case, then everything else you did was right. So I gave you like 4 to 5 for this question, right? Because, but still, there was sort of a transcription error at the start, which did result in the question being wrong according to the key, of course. But all the work you did past that was all totally good workings. But one consequence of the fact that you put the side over here as a known one meant that you could use sine law. Whereas, as we see here, if we write it out like this, we actually can't use sine law because we don't have this side over here, and we're not told this is a right triangle. If we were told it was a right triangle, then we could indeed go ahead and figure this side out, but we're not. We're not told that. We can figure the side out anyway, but to do that, we have to use cosine law, right? So we know that cos, sorry, I don't need to start off with cos here. I'm going to do e squared equals d squared plus f squared minus 2df cos e, right? Because it's very important that that this angle here, e, right? This is the one that's opposite side lowercase e. There we go. That's not water, that's coffee, but it's got a high amount of water content, right? Water and caffeine, how can you go wrong? The two of the most important food groups. So now I can go through and sort of fill this in with what I know, right? So I don't know e, so this is going to stay as e squared. But then I know that I know that side d is 21.4, so that's squared, plus side f is 15.8, so that one's squared, minus 2, 21.4, 15.8, and then cos, don't mind me cramming this in here, 56. That's not actually down below, it's just because I'm running out of space on my paper. Oops. What a rookie mistake. So e squared, let's get my old pal here, TI-84, the mathematical Game Boy, right? Which, I mean, I know I keep saying that, but it's wonderful, right? It's a dot matrix screen. I finally cracked the code is the way I like this calculator so much. Because it looks like an old school Game Boy, right? Like, how could you go wrong? Right? Where it's a screen of, green and also green. So that's going to be 707.6. It's going to be that one there. Minus 2 times 21.4 times 15.8. Yeah, I'll do this out a little bit slower. 676.24 times cosine of 56, which I haven't found yet. So e squared is going to equal 707.6. Subtract that number times cosine of 56. So it's going to be minus 378. I'll call it 378.1. So e squared is going to be 329.5. And then the root of that last answer is going to be e gives us about 18.15. I'll call that 18.2 because that is what it would round to. 18.2 centimeters. Okay? So now that we have that one, well, now I can go ahead and figure out all the angles as well, right? Because it told us to, see, what did the question tell us to do? Draw a diagram. It says solve DEF. Okay. So if it tells us to solve DEF, that's code for find all the unknowns, every one of them, right? So I'm going to go ahead and I'm going to find F here now as well. So I'll do that in blue over here, right? Or yeah, so this is going to be angle F. Now the thing is, now I have this 18.2 over here. I could use sine law to find the next one if I wanted to, and yeah, I think I'll go ahead and do that. So I'm going to do so remember it's going to be E over sine E because that's the pair that I have, right? That's going to equal F over sine F, like so. So then that's going to be 18.2 over sine 56 equals 15.8 over sine of F, and we don't know F yet, right? So once I can cross multiply these guys, and I'm going to have 18.2 sine F equals 15.8 sine 56, because that was a cross multiplying step. I'm going to now divide. Sine F equals 15.8 sine 56 divide by 18.2, which you might have known we were going to get to when we started this one, but it doesn't really matter. Like I do like to write out all my interstitial sort of steps, all the things in between. And I'm going to go ahead and grab my Game Boy, and 15.8 sine of 56 is going to be that. We're going to divide that by 18.2. And we're going to get sine of f is equal to 0.7197. So then f is going to be the inverse sine, right? Remember our inverse sine function? That's this down here, right? So I'm going to, my calculator is going to be second function sine of the answer. And then that's going to be 46 degrees. Then to find the last one, of course, the last one is going to be fairly easy, right? So D is going to equal 180 subtract 56 and subtract 46. So 56 plus 46 is 102. So D then should be 78 degrees, right? So there we have it. All right, so that is question 11 then. And I think there was one other one that I wanted to get to on here. Yes, I kind of wanted to do question 12. Okay, so let me go back over to my document display so we can see this a little bit better. Question 12 is another one, Betty Ann, that you did very, very correctly, except for one small little thing. So you got the majority of the marks for this question. It said a radio tower is supported by two wires on opposite sides. On the ground, the ends of the wires are 46.5 meters apart. The angles of elevation are 62 and 67 respectively. Determine the length of the longest wire and the height of the tower to the nearest tenth of a meter. Okay. I'm going to grab a different page here to do those on. So this is going to be Math 2101A, Unit 3. Okay. Number 12. I'm going to go ahead and I'm going to use, you know what? I'm just going to draw this diagram nice and big because this is the last question I'm going to do. This is the only, well, not the last question I'm going to do for today. The last question I'm going to do for this topic. So it'll be the only one that I do on this sheet of paper. So let's go ahead and draw that one out nice and large. Here is our radio tower here in the center. And then the sort of antenna coming up from the top of that. All right, it's a good enough. It's a good enough tower. Right, there we go. With looks kind of like Solaire's son from Dark Souls. Right, that's a good reference. If anybody, maybe that should be required reading. Everyone has to play through Dark Souls 1 before they can finish the program. That would increase the difficulty of the ABE program substantially. Let me tell you, beating Dark Souls 1 is probably harder than most of these courses. But I mean, all you do is just strap on a shield, right? You just strap on a shield and hold that button down. Then you just get that L button going, and then you just R1 hero, right? Bam. Nothing to it. Anyway, angles of elevation for the wires are 62 and 67. So this is wire 1, so this is going to be our 62 degrees. This one here is going to be our 67 degrees, right? And then the wires are 46.5 meters apart, so at the bottom it's going to be 46.5 meters. Now determine the length of the longest wire and the height of the tower to the nearest tenth of a meter. Okay. So there are several ways that we can go about doing this one, right? The part that I want to show, well, let's see. This angle up here, right? Now, Betty Ann, you noticed correctly that you could find that angle by doing 180 minus 62 and minus 67, right? Which is just 180 minus 129, which is going to be 51 degrees, right? So we know now that this top up here is 51 degrees. So now we have a triangle, right? And we can use sine law to find whichever side that we want. Now, the only thing you did wrong in this question is that you found this wire and you said that that was the longest one. But we know that this wire is actually the shortest wire, the shortest of the two, or the shorter of the two, right? Because remember this math problem from way back? Yeah. Yep. Yeah, you did this one. Did this a while back. Hey, it was a ways ago. You did this one. But this wire here is opposite a 62-degree angle, right? But this wire here is opposite a 67-degree angle. And we know that the side that's opposite the biggest angle is going to be the biggest side, right? So we know that when we have to find our biggest angle, we're actually looking for wire 1 over here, right? But write down our sine law. We know A over sine A is equal to B over sine B, like so, right? So we have our 46.5 over sine 51 is going to equal some unknown amount over sine of 67, right? Because I'm going to go ahead and find this wire over here because I know it's opposite the biggest angle, so it's going to be the biggest side. So do our cross, or to get the 67 out of there, 46.5 sine 67 divided by sine 51 equals x. Now my calculator. There we go. So about 55.1 is equal to x. So we know that this side over here is going to be about 55.1 meters, right? And we know that's the longest, despite how my triangle is drawn, and despite how the diagram is drawn, because again, right, teachers are sneaky. The diagram doesn't necessarily correspond directly to what you're being told. This side here is actually the longest side of the triangle because it's opposite the biggest of the three angles, right? Then we were told to find the height of the tower, right? So how are we going to go ahead and find the height of the tower? Well, there's a whole bunch of ways that we can find that one, right? Because now the tower, the tower's going to make a right angle with the ground now, isn't it? Right? Down there like so. That's going to make a right angle with the ground. So to find the height of the tower, I can actually go ahead and use just normal old trigonometry, right? Not even sine law and cosine law. I can just use the basic ass, sine and cosine, right? Because now we've got this sort of triangle where this is a 55.1, this is 62 degrees, and we need to find this side here, right? Now you did do this correctly, so again, right, I gave you most of the marks for this question, just you picked the wrong wire to find. But everything you did was just for this side, but it was still correct because you got the correct height, right? But I'm going to go ahead and use this one now. Remember that our sine ratios, some old hags can't afford husbands till old age. There we go. So those are our three, right? We have the hypotenuse, we have an angle, and we're looking for opposite. So we know that we're going to deal with sine here, right? So I know that sine of 62 is going to equal x over 55.1, right? Or if I just do the multiplying here now, 55.1 times sine 62 is going to give us x. So 55.1 times sine 62 is going to be about 48.7. Right? So now I know that the height is about 48.7 meters. Okay. So that's all the stuff that I wanted to cover for your test there, Betty Ann, or activity. Well, that was a really good job on that one. So I will send you the notes and your grade shortly once I'm done here. There was one other topic that I was asked to go over, so I'm going to do a little bit of review for solving two-step equations. Okay, so let me just pop back over to my intro screen. I'm actually going to, like I said, I'll skip the units of area for today because I do want to wrap it up in around 15 minutes as normal. And then got other stuff to get to, especially where it's nearing the end of the month. I have quite a lot of paperwork, etc., to do, right? Let's pop back over. Let's look at the one. Yeah, let's look at this one with the quad in it again, right? I do approve of any major city where you see people, just driving around on quads. That's good. That's a good sign. Something cool happening tomorrow. SpaceX is launching NASA astronauts from Florida tomorrow. Oh, cool. Okay, so NASA is starting to use SpaceX to bring people up to the ISS, I guess, the International Space Station. That's pretty cool. Yeah, because I guess they can do it. They can do it for a lower cost. Okay. Yeah, nice. Yeah, I do. I have a book actually. I have a picture book. Uh, I mean, calling it a picture book is maybe a bit diminutive, but it's the book from Chris Hadfield, right, with all his photography from the International Space Station. It's pretty amazing. You see some of the pictures that he can get because like the International Space Station is actually in a really low orbit, right? Because it's just kind of falling. It's falling so fast that it misses, right? That's sort of what orbit is like, right? You're just falling so fast that you miss the planet and you just loop around, right? So it's tearing through space, like it's moving overhead at a very fast pace, but it's not all that high up. So like compared to like a satellite or something, right? So the photography that he got from the International Space Station is incredible. Maybe I can show a bit of that on stream sometime, but that's like my coffee table book out in my living room, right? That and that book and like the big compilation of Calvin and Hobbes and like a big compilation of Peanuts, the comic strip, not the legume. Anyway, so I'm going to go on and do a little bit on solving two-step algebra equations. This is relatively basic stuff, but it is really fundamental, really important for students to get. So I will do a few of these ones here, right? Going to switch back over to my working display. Zoom in a little. So I'm just going to go down and I'm going to do a few of these ones off of this sheet. This is just a sheet that I generated from mathaids.com, right? Which you can see down below me here in my FAQ. I do mention that one as a very good source for practice work, and it remains that, right? It's a great place to get any sort of to get just like extra math drills that are procedurally generated, but also come with an answer key and stuff like that, right? It's fairly straightforward and user friendly. But this is going to be solving two-step equations. I'm going to go through these fairly quickly unless anyone has a question. The student who asked for this, I don't believe, is in chat. But if anyone in chat has a question about these, just fire one off and let me know. But I'm going to go through these relatively quickly because this is just sort of good old meat and potatoes algebra, right? The basics that you need to know for every single course that you're ever going to do in this math program. So when we're solving just means get the variable by itself, right? So we always have to do the opposite of whatever's here. So here we have 6 plus k, which are both divided by -4, equals 19. So we got to get rid of this -4 over here, right? So this symbol means divide. I know at first that can seem a bit confusing, right? It's a fraction, it's not divide, but that's what a fraction is, right? A fraction is the numerator divided by the denominator. That's what it means, right? So to get rid of this -4, what I'm going to do is multiply both sides by -4, sorry. Now you're not always going to write this step in, but I am going to. Right? So just to show you what I'm doing is I'm multiplying both sides by -4. So I'm going to end up with 6 plus k on this side because the -4s are going to cancel. And over on this side, I'm going to have, well, 19 times 4 will 20. 20 times 4 will be 80. So then 19 times 4 is 76. So this is going to be a -76. So 6 plus k is -76. So we know that k is going to be -76 minus 6, or k is going to be -82. And just again to show you some of the usefulness of math aids, I'm going to scroll on down here. There we go. See, k is -82. So it comes with an answer key. So if you want to practice any questions like this, easy peasy, go on there, generate a list of them, and then there you go. You've got a PDF with a bunch on there. You can make as many as you want. So again, right, I'm going to Just going to do a few across here. So here we have a third of h minus 15 equals negative 18. And remember, our goal is always to move pieces away from the variable, right? So here now we've got a third and we've got a negative 15 over here by the h. Now I can move the third out of the way first, but it's a little bit easier if I move the subtraction, get rid of this one, right? Because to get rid of a minus, well, that's fairly easy to know, right? The opposite of minus is plus. So we're always going to be doing the opposite, right? So what I'm doing is I'm doing the opposite of that to both sides of the equation, and the goal is to get these two guys to go away. So I'm going to have a third h is going to equal negative 3. Then this is multiplying by a third, right? So then what in the world do I do? How do I get rid of multiply by a third? Well, there's a whole bunch of ways you can think about this one. You can think about this as just h divided by 3, because what this really is it's multiplying by 1 and dividing by 3. Or you can think about it as a fraction, right? As multiplying by a third. And what's the opposite of multiplying by a fraction? Well, dividing by the fraction, yes. But when we divide by a fraction, what are we really doing? We're multiplying by the reciprocal, which is the fraction flipped, right? So if I have a fraction like this, what I'm going to do is I'm going to multiply both sides by the reciprocal. Now, yes, I don't need to write in the over 1 here because every whole number is over 1. But I'm going to go ahead and do it just to show that what I am doing is multiplying by the reciprocal of this fraction. So now I'm going to end up with h is equal to negative 9. And if I scroll on down here, I'm going to see h is equal to negative 9. There it is. Right? So let's do a few more of these. But I'm not, I think there's 10 on this page. I'm not going to go through and do all 10, but I'm going to do a few more. Number 1. Yep. What's up? Number 8. Burp. Explain again why the negative 4 cancels. Okay. Yeah, so over here now, this is not a minus 4. I put it in the bracket here to make it clear that I'm multiplying by a negative 4, right? That is one of the limitations of the way that we write math, is that negative and subtract have the same symbol, which is kind of annoying in retrospect. Like someone should have fixed that in like math version 2.0, right? But this is not a subtract 4, this is a multiply by negative 4. Right? So the negative 4 this is divide by negative 4, this is multiply by negative 4, so they're going to cancel. Same reason over here, this one is multiply by negative 4, so we end up with negative 76, because we're doing 19 times 4, except it's a negative 4. Right? I know it does, this looks like I'm saying subtract 4, and if this was a subtract 4, that wouldn't work there. And this one is going to be b plus 25 over 9 equals 8. Right? So this is a good one to mention the previous one, yes. Because now I'm going to do the same sort of deal, right? Because here I'm dividing by 9. So what I'm going to do is I'm going to multiply both sides of this equation by 9. So it's going to be times by 9, and this one is going to be times 9. Now what's going to happen here, this 9 and this 9 are going to cancel, right? Because divide by 9 and multiply by 9 are just sort of two halves of the same coin, right? So they're going to cancel. On this side, I'm going to be left with b plus 25, and on this side, I'm going to be left with 72. So now when we have something like this, it's probably fairly clear now that what we should do is subtract the 25, because you can think of it as some number plus 25 gives us 72. Well, we know that number has to be 25 less than 72, right? Because that just makes sense. Some number plus 25 gives us 72. Well, that number is 25 less than 72. So sometimes the way this is taught, and I had colleagues when I was in the UK sort of say that they explained it to the students this way, and it does make sense, right? That what you can do is you can move this part over to the other side, but when you move it to the other side, it becomes its opposite. Technically what we're doing is we're taking away a 25 from both sides. So kind of the way I was modeling it here, or over here, right? This is technically what's happening. But you can think of it as sort of that one moves over there. But we end up with b is equal to, so 72 minus 52 minus 5, so that's going to be a 47. So again, right, if I scroll around, there we go, 47. Okay, so let me just do, I'll do 4 and 5 for sure. Then we'll see how we're feeling about finishing these guys off. 2s plus 13 equals 10. Well, we know that 2s plus 13 gives us 10. So what's 2s got to be? What I'm going to do, like I said before, right, is I'm going to be subtracting a 13 from both sides. Because the idea is I want to cancel out and get rid of the pieces that are over here next to the 2. And to do that, here I'm going to have to subtract. Right, so this plus 13 and this minus 13 are going to cancel each other. I'm going to be left with 2s. Now 10 minus 13 is going to be a negative 3. So 2 times s is negative 3. What I'm going to do for my next step is I'm going to divide both sides by 2. The sign's reversing when you move it to a different side of the equals, I think, is probably the most important algebra rule. Oh yeah, absolutely it is, of course, right? Because, I mean, managing your signs, your positives and negatives, is trickier, for sure, than a lot of the stuff that we're doing, yeah. And then knowing that when this moves over here, it becomes its opposite. Yeah, exactly. Right? That is really, yeah, the summary of the most important rule, I would say, for sure. So this 2 is going to cancel with that one. We're going to be left with s is negative 3 over 2, or just negative 1.5. Whatever we want to call that. We could leave it as negative 3 over 2, and that's totally fine. Or we can take negative 3 divided by 2 and get negative 1.5. We see down here, the script that created this page did indeed reduce it down to negative 1.5. Question 5, negative 19 plus 4r equals 26. Right? So now, I do like to get rid of the plus and minus first. We could get rid of this multiply first, but that actually sort of makes more work for us because we had to be multiplying each term. What I'm going to do is I'm going to add 19 to both sides. Right? Now this minus 19 and this plus 19 are going to cancel each other, right? Because they're going to, negative 19 and positive 19 make 0. And this side over here is going to be now 45. 26 plus 19. So then, 4r divided by 4 is equal to 45 divided by 4. So r is going to equal 45 over 4, or that's going to be 11.25. Now you can do that one in your calculator. I'm not going to expect you to do that one in your head or something, but I did it just by thinking that, well, 44 over 4, I know that's 11, 44 divided by 4, and then 1 divided by 4, well, that's a quarter. It's 0.25, right? I knew that one already. Right? That's why we call, something that's 25 cents is called a quarter, because there's 4 of those that make $1. There we go. We got question 5. So how's about I do one more? One more from over on this side. What's a, oh, there's a good one. There's a good one to do. Yeah, number 9. So I'm going to skip ahead and do number 9 off this sheet, and then that'll probably be enough for a brief review on this topic. So number 9 over here is negative 24 plus 7 over 9d is equal to 26. So to start off, just like I was doing in the other ones, I'm going to get rid of this negative 24 first. So it's going to be negative 24 plus 7 over 9d plus 24 equals 26 plus 24. Right, so those cancel, and we'll be left with 7 over 9d is equal to 50. So now what do we do? Right? Well, now this goes back to what I showed in question 2 up here. We're going to have to multiply both sides by the reciprocal of this fraction, right? Because that's how we cancel fractions. You can also think of it as, like I said, this is 7 over 9 times d, right? So we had to divide by 7 over 9 next, which is the same, as you saw in the refresher math courses. Dividing by a fraction is the same as multiplying by its reciprocal. So what we're going to do now is multiply by the reciprocal. 7 over 9d times 9 over 7 equals 50 times 9 over 7. So now we're going to have d is equal to, now when we're multiplying by a fraction, what we do is we multiply by the top, then we divide by the bottom, right? So here now we actually have 50 times 9, which is going to be 450, and that's going to be divided by 7. Now I definitely don't know what that is off the top of my head. So here we go. 450 divided by 7, 64.3, I'll call that. So d is equal to 64.3. Now, on your in your activities and stuff like that, you do have calculators that you can use, right? Because every course we offer, except for one, except for the very first level 2 course, excuse me, but every other course we do, you can use a calculator for, and this one is no exception. 64.29, they called it. Okay, well, excuse me, I rounded it to 64.3. Well, they were a touch more. They rounded a touch less than I did. Maybe they were a bit more precise. But anyway, I think that should be a good amount for today to cover all the topics that I had to get to. Renetta, if you are there in chat, sort of waiting for me to cover unit conversions, I can do some of those there now if you let me know. If not, I'll link you maybe to some of the sort of the times we've seen these ones previously. But I think you've probably got a good few examples of those ones to look off of as it is, right? So if you look back over here to this quad next to this Greek market where I got my my knife, right? This guy. Oh, maybe I'll put him in the shot. Put him back into my shot over here, right? I still like this one. Look at that, right? It's not super sharp anymore, although I do keep it sharpened reasonably. But the most important part is still that saw, right? Just to recap some of my show and tell from earlier. Look at that. That saw part, oh my God, so useful. That's why I carry this knife on every hike I'm on. This cuts firewood like a mother. And then that opens up cans and stuff easily, and it's a screwdriver on the tip there in case you ever need it. It's great. And then other pieces of wonderful show and tell like this piece of beautiful Aboriginal sort of soapstone and antler art from made in Swedish, in the north of Sweden, I believe, by I can't remember what the peoples were called now, but you can see the artist's signature there on the bottom. It's quite pretty. I have quite a few other nice pieces of show and tell that I will get to eventually. Right? Got my some of the coins that I talked about. But for today, for this show and tell stream, I think we're just about done. So thanks for joining me today. I hope you found it interesting and compelling and entertaining and captivating and, sleep-inducing. All right? I mean, it was at least one of those. So, thanks for joining me. Stay safe and hope to see you again tomorrow.